No. I'm not.
I feel like this is somewhere.
I'm moderating the. I'm looking at the slide.
Yeah, and Sebastian, speaker can also use this if we need this.
And ultimately.
Good morning, everyone. I hope you're all well rested and excited for a fantastic day of talks. I just have a very quick announcement, which is that today between 11:30 and 12, we have a discussion sessions. We have 7 topics. You can sign up on Slack. There are groups in person. So if you pick a topic and the topics are on Slack, then in person you can follow those lovely printouts and go sit with your friends and talk about those topics. One of the topics is choose your own adventure. So if you want to not do any of those, but do something else, go there. Thank you. Bye.
Okay, so I think we're going to go ahead and get right into the first session. So welcome Matt Hosek, who will be talking about the Galactic Center.
If you can take one of these, and then
Close that. Yeah.
and then you can just pin it on your.
Okay, good. Yeah. I think so. Let's see. Yeah, perfect. Can everyone hear me? Great. Okay. It looks like you got a thumbs up there. Let me just get this set. And clicker. Perfect. Okay, great. So hi, everyone. Thanks to the organizers for giving me the opportunity to speak today. My name is Matt Hosek. I'm a postdoc and Brinson Prize Fellow at UCLA with the Galactic Center Group. And today I'd like to talk about some of the exciting opportunities that the Roman Space Telescope will provide us to study the large-scale kinematic structure of the Milky Way's Galactic Center. Okay, so for the purposes of this talk, when I say galactic center, I'm referring to the region that extends out to a radius of 150 parsecs from the central supermassive black hole. This region is sometimes referred to as the central molecular zone. That's because it contains upward of 80% of all the dense molecular gas in the entire galaxy in this region. Now, at a distance of just 8,000 parsecs from our sun, our galactic center is 100 times closer than any other galactic nucleus. Right? So that means it's the only galactic nucleus for which we can study the stars in a resolved manner and with high detail. And when we see our galactic center, we find that it is amazingly complex with many different components and features. For example, at the very center, we have Sagittarius A star, our central supermassive black hole that's 4 million times the mass of our sun. And it dominates the gravitational potential within the central half parsec of the galaxy or so. The rest of the region is dominated by two main stellar structures. The nuclear star cluster, or NSC, which is the densest and most massive star cluster in our galaxy, with 10 million solar masses within a radius of 5 parsecs from Sagittarius star. And then the nuclear stellar disk, or NSD, which is a more extended structure of about 1 billion solar masses that's elongated along the galactic plane and reaches to a radius of about 100 parsecs or so. Now, both of these populations are old star populations with ages of about 5 to 10 billion years old. But there's more than just old stars at the galactic center. There's also many examples of recent and ongoing star formation. In fact, the galactic center is one of the most actively star-forming regions of our galaxy today. And two prominent examples of that activity are shown here, the arches and quintuplet clusters. With ages less than 5 million years old and masses of 10,000 solar masses or so, these two clusters are among the most massive young clusters known in the galaxy. Okay, so why do we care? Well, when we look at galactic nuclei in other galaxies, especially those in other spiral galaxies, we find that they share many of these same features and characteristics. Right? We see central supermassive black holes and nuclear star clusters and disks and young clusters. Right? So what that tells us is that our galactic center serves as a valuable template for understanding the evolution and formation of galactic nuclei. Because again, the galactic center is the only place where we can study these features in very high detail. For example, we can measure their proper motions. So JWST has been very, very exciting, right? With its high sensitivity, spatial resolution, and wavelength coverage, it really has enabled many new investigations at the Galactic Center. In fact, by my count, there's something like 9 ongoing JWST programs in the region. And programs are still ongoing, but they cover a wide variety of topics, some including star formation, right? How do stars form at the Galactic Center? What are the gas properties, right? What are the details of the stellar populations at the very center of the galaxy? Their kinematics, density profiles, and so forth, right? So these programs are so far really clustered around the highest density or highest extinction regions toward the Galactic Center, which is where JWST, with its fantastic capabilities, really makes it accessible to us. Right? But looking at this, you'll see that in terms of spatial coverage, JWST can really only observe a small region of the Galactic Center as a whole. That's shown here. These cyan boxes represent the NIRCam A and B modules. Right? So although with JWST we can observe the small region to very high detail, it's hard to get a picture of the large-scale structure of the region. Right? And this is especially true if we want to measure proper motions, which of course would require multiple observations across the entire region. But this is where Roman can come in. Right? With just 5 pointings of the wide field instrument, you could image the entire, nearly the entire Galactic Center region. Right? With HST resolution and precision. Right? That makes Roman uniquely suited for large-scale dynamical studies of the Galactic Center. Right? We could measure proper motions out to radii of 150 parsecs from Sagittarius star. Now we're starting to reach size scales where we observe these features in other galaxies and other galactic nuclei. But we have all the detailed proper motion information. So to quantify this a bit further, this is a plot of number of stars observed as a function of observed area for current proper motion surveys of the Galactic Center compared to what we could do with Roman. The black points down here, these are proper motion surveys taken from the ground. Right? When you observe from the ground, we have to correct for the turbulence of the Earth's atmosphere in order to get the spatial resolution to observe the stars of the Galactic Center. And the penalty you pay for that is that you're really only able to get astrometry over a relatively small field of view at once. That's why the ground-based surveys are focused on this part of the lower left part of this plot. Right? We do better when we go up to HST with these blue points, because now we're above the atmosphere, and we can get precise astrometry over a much larger field within a single pointing. But the red stars show what Roman can do. Right? With the 5-pointing Galactic Center mosaic, we expect that we could measure the proper motions of 16.5 million stars in the Galactic Center region. Right? And cover an area that's at least 10 times larger than any other proper motion survey. And we know from our experience with HST that Roman can deliver high precision astrometry at the Galactic Center. in particular from our WFC3IR observations. We know we can achieve, measure specific stellar positions to an accuracy of about 0.15 to 0.4 milliarcseconds. Which now, okay, if we take that, let's assume a general observer, general astrophysics survey of 3 epochs of observations over 5 years, right? That means we could measure proper motions to a precision of 50 to 100 microarcseconds per year, right? That's a velocity precision of 2 to 4 kilometers per second at the Galactic Center. This gets even more impressive when we consider just taking even just one of the fields, the centermost field, and add it as part of the galactic bulge time domain survey, which we talked about a bit yesterday. Right? Because of the high cadence of these observations, we expect that we would be able to get proper motion precisions of 3 microarcseconds per year, now 0.15 kilometers per second, which is really incredible. In fact, adding the Galactic Center to the time domain survey would enable a whole host of science cases, not just those driven by dynamics. And if you're interested, I encourage you to take a look at our white paper that Sean Terry, myself, and our collaborators recently did, which should be posted to archive soon. Okay, so at the very end, I just wanted to highlight 2 science cases, which I think nicely shows the synergy between JWST and Roman. The first one is the formation and evolution of galactic nuclei. In particular, this NSC and NSD structures I mentioned earlier. Now with JWST, right, we could characterize the stellar populations, we could go really deep over specific regions, and we can ask questions like, well, what triggers or suppresses star formation at the Galactic Center? And what is the star formation history of the NSC and NSD? But we come in with Roman with this large field kinematic survey, and we can ask questions like, well, what is the kinematic structure of the NSC and the NSD? What is their relationship? And what does this indicate about their formation mechanisms? We can also ask, well, what is the total mass distribution and gravitational potential in the Galactic Center region? Something that is surprisingly uncertain, right? And so in order to answer these questions, we need proper motions coverage over the largest extent of these structures that we can do, right? So this is really in the Roman regime. The second science case I wanted to bring up was studying the life cycle of star clusters at the Galactic Center, like the Arches and Quintuplet. Now, because of the steep gravitational potential, these clusters are only expected to live for 10 to 20 million years before they get tidally disrupted. So even now, even at their young age, they're expected to have large tidal tails, like these magenta ovals here, but it's never quite been observed. So again, what can we do? Well, with JWST, we can characterize the stellar populations of the clusters themselves. We can ask questions such as, what is the stellar initial mass function of star clusters at the Galactic Center? Right? And is there evidence that low mass star formation is suppressed in this region, possibly due to the extreme star forming environment? Right? But with Roman, looking at these clusters, again, we get the larger scale kinematic view. We can look for, detect, and characterize for the first time these tidal tails. And so we can ask, okay, well, how do star clusters evolve and dissolve in galactic nuclei, right? Do they actually follow what the models predict would happen? And we can also ask, well, how has this tidal stripping impacted the observed cluster population that we see today, right? Because this tidal stripping is something we're going to have to take into account if we really want to properly derive the initial mass function from our JWST observations. Right, so just to finish up, I would say I'm very excited. I think Roman will enable a new era of science at our Galactic Center. I hope I've convinced you that Roman is uniquely suited to do a large-scale dynamic study of the Galactic Center. Right, we're talking about the proper motions of 16.5 million stars in this region. And so Roman will really provide a large-scale dynamical context for many of the really exciting studies going on at the Galactic Center with JWST and other instruments. And so with that, I can take your questions, and thank you very much.
Is this on? Yeah. Okay. Is there any questions in the room? Okay, let's go online while the mic gets over there. Oh, nothing online. All right, you're up.
first off, you need a reference grid of background quasars or something, and does that exist, or is there precursor work that has to be done to get that?
That's an excellent question. And I think, do folks online hear the question as well, or do I have to repeat it, or? Oh, okay, just making sure. Perfect. Yeah, so excellent question. So it turns out at the Galactic Center, we can actually use Gaia stars to define our reference frame, to define that coordinate system. Now Gaia can't see stars at the Galactic Center directly, right? It's way too extincted. It's only a visible telescope, but it can observe stars in the foreground. And so there have been several projects, some led by myself, some by others, that have used like Gaia foreground stars to derive absolute astrometry from HST WFC3 IR observations of the Galactic Center. So the answer is those reference sources, they do already exist. We don't have the background quasars, but Gaia does a very good job of defining this reference frame. So.
Okay, any other questions in the room? We have time for one more.
Do you see a role for the slitless spectroscopy mode in the Galactic Center?
Ooh, that's the slitless spectroscopy mode. I think that's, let's see, that's resolution of 600?
There are two. There's I guess it's RF300, and then there's an RF-ish or something. So there's, I would imagine a higher resolution would be more. But if you haven't thought about it, it's fine. It's just wondering.
No, it's a good question. I haven't thought about the slitless spectroscopy mode that much. I'll be honest, I'll have to think about it more. I know for the centermost region, when we're characterizing stars, are they old, are they young, what are their properties, we usually require a spectral resolution of like 3,000 or 4,000. We're using OSIRIS on Keck. I'd have to think a little bit more about but it's a great question. What could we do with slitless spectroscopy? So I'll have to think about that.
A quick question. So is getting distances going to be a problem? Do you really need, like you said, kilometers per second in your, like you have proper motions, but to convert them to velocities, you will need distances. So
yeah, that number was assuming a distance of 8,000 parsecs, right? So that's like the average star at the Galactic Center. I mean, when we're pointing toward the Galactic Center, right, the density of stars is so high that they really dominate the field. There's some foreground. We can do color cuts to remove them. There's definitely some distance dispersion that isn't part of, a point of uncertainty, but a lot of these stars, are around that 8,000 parsec distance. So that's where those numbers came from, that assumption.
Okay, I think that's about time for the session. So remaining questions, let's continue in the Slack.
Great, thank you.
Okay, and the next talk will be a recording where Ankita will talk about the origin of metal-rich stars near the sun. And for this, there's one other recorded session in this session. So for both of those, we'll show the recording and then go to the next one. So add questions in the Slack, and I think and they will answer them as their time zone permits.
Hello everyone, my name is Ankita Mondal and I am an MSc graduate from Tezpur University, India. Today I'll be presenting before you in brief about my current research project on the origin of metal-rich stars near the sun that I have been pursuing after the completion of my master's and is jointly supervised by Professor Kenneth Freeman and Dr. Michael Hayden. Understanding the formation and evolution of our galaxy Milky Way is, I believe, one of the major challenges of the modern astronomy. The close proximity of our galaxy allows for detailed studies of its structure, star formation history, and chemical composition, thus providing valuable insights into the process of galaxy evolution. So, through galactic archaeology, we actually use the fossil records of the stars that have been born throughout the history of the Milky Way to figure out how it has evolved over the ages. The kinematic plane of stars near the Sun shows a wide range of complexities of the structure of our Milky Way, and this region near the Sun, better termed as the solar neighborhood, contains stars spanning a huge range in age and metallicity, about which I will be talking in the coming few slides. Now coming to our main topic, that is the supersolar star problem in the solar neighborhood. So we actually find stars of all ages are found in the galactic disk near the Sun, young and old. But the most metal-rich stars with FEH greater than 0.1 could not have formed near the Sun, because the interstellar medium near the Sun is not that metal-rich, and so they are believed to have migrated from the inner galaxy, and there are at least 3 ways for that to happen. The widely believed radial migration, which is driven by transient spiral structure, and these transients actually moves the stars from one circular orbit to another circular orbit at larger radius. Next, a major event with time-varying change in the asymmetric potential is possible, and one such example would be the formation of the bar, which would have been a big event that might have caused a lot of migration, as we find in simulations. The third way possible is that the stars can migrate as they can be trapped near co-rotation by neutral points in the bar, which can waft the stars into the solar neighborhood from the inner galaxy on eccentric orbits, which I'll talk about in the next few slides. So the motivation behind our work is that how these supersolar metallicity stars reach the solar neighborhood is an open question, and we are trying to examine the motions, ages, and metallicities of the supersolar stars and look for effects that could be associated with the migration of these metal-rich stars from the inner galaxy to the solar neighborhood. So we have used data from Apogee, which observes stars in the near-infrared age band, of which most of them are red giants, and from Gala, which observes stars at optical wavelengths. For the ages, we used chemical clock ages, which are determined for a large fractions of stars in the Gala survey with well-measured chemical abundances. The training set contains MSTO stars, which are the main sequence turn-off stars, with precision ages determined from isochrone matching. The ages for apogee giants are based on carbon to nitrogen ratio, calibrated on stars with seismological ages. We have also used value-added catalogs that contains data for parallaxes and transverse motions from Gaia DR2. Now coming to the eccentricity distribution. So the orbital eccentricity near circular or elongated is a very useful indicator of stars' dynamical history, and it varies most strongly with a star's age and therefore as a function of alpha Fe. Young stars with low alpha abundance tend to have circular orbits with, that is, E less than 0.15, while older stars with higher alpha abundance tend to have more elliptical orbits with E around 0.35. So the higher alpha abundance and higher eccentricity of older stars with lower angular momentum suggests that they originated from the inner part of the galaxy. The stars with high metallicities than the local ISM makes up a significant portion of the stars in the solar neighborhood. So the more than 70% of these stars have low eccentricities, suggesting that they might have migrated to the solar neighborhood rather than born there. The low random motion of these stars indicates that they did not travel far from their birthplace, which is likely at radii much larger than the solar neighborhood based on their metallicities. So here are a few of my plots from Gala survey made with respective curves. So for Gala, we considered stars with FEH greater than 0.1, distance from the sun less than 1 kpc in different chemical clock age means. We find a small increase of eccentricity with age, as we might expect from a population that migrated from only a small eccentricity and then suffered a small amount of local heating as it aged. Most of the stars are in the older age groups, which either suggests that there are few young stars with these characteristics in the inner galaxy, or maybe that the radial migration is not so active now as it was in the past. These are some similar figures made with apogee data for stars FEH greater than 0.1, Z less than 0.25 kpc in different radial bands. Here we too find a large number of stars in the solar neighborhood in the third panel. Yes. So coming to the second facet of our work about Hercules. So the Hercules stars are actually a group of stars believed to have originated near the Mars co-rotation radius in the galaxy. So these stars are expected to be more abundant in the metal-rich populations and have a broad range of metallicities similar to those found in the inner part of the galaxy. So this is a plot using Gaia DR2 data for local neighborhood around us. Along x-axis is the outward velocity and along y-axis is the angular momentum. What shows up here is we see a feature which is long known as the Hercules stream or moving group and can see the zero output velocity. The stars are predominantly going out, and it's also believed that these Hercules stars are trapped orbits around the stable Lagrange points, and they have no particular chemical properties but just a random collection of stars. So our possible interest of Hercules to the supersolar stars is to find if Hercules is also seen in the supersolar stars. Here are a few of my plots for velocity distribution with VR on x-axis and V5 on y-axis. For stars with distance from the Sun less than 1 kpc, FEH greater than 0.1 for different age pins. In the top right plot, we can find Hercules moving similarly to the other field stars in the solar neighborhood, and this bottom density plot depicts the same more clearly. So with this, the results of our work so far have been that the eccentricities for the supersolar stars are low, as consistent with radial migration, and there are supersolar stars in Hercules moving similarly to the other field stars. Our future plan includes to investigate the distribution of orbital actions for the same set of stars within 1 kpc from the Sun. Thank you so much for your attention.
Okay. Ankita, you're online? If you are, we can take questions. If not, then not online. Okay. Great. So post them to Slack and she'll answer when she can.
Oh, wait, this one's.
I can share my screen.
Okay. You can go ahead and share.
Okay, so next up is Benne Holwerda, who will be talking about brown dwarfs and red dwarfs and Webb and Roman.
All right, thank you all so much for being here this morning, and thank you for having me. So I'll talk about brown dwarfs with JWST and Roman data. So this is the motivation. Why would you count stars? If you remember from your astro classes, wasn't that a terrible idea at the beginning of the 20th century? But you can, if you know what you're doing, you can actually infer the shape of the Milky Way that way. You just sort of, similar to in a crowd, for example, you're in the auditorium right now, and if there's more people to the left of you than to the right of you, then you know you're not at the center of the room, if you couldn't see the edges of the room, for example. So it's best to go to near infrared to avoid dust issues, and I'm actually interested in, let's see, the lowest possible mass for stars rather than going for giants or for solar mass stars. So you get the most common stars and you get much better statistics. Now, why are we doing that? Well, Ross Ryan proposed a while ago that as these small stars, or not quite stars, stop their fusion, they start cooling, they basically become a later spectral type, so they cool as they age. And at the same time, this whole population gets kinematically heated. So there should be a relation between spectral type and scale height. And then this is sort of my summary plot of everything we knew until a few years ago. And you can see that we're mostly measuring these things at the M types, and our measurements of the scale height are all over the place still. But it would be interesting to see how spectral type and the structure of our Milky Way are related to each other. So what can you do with James Webb? Well, for one thing, James Webb is a fantastic instrument for just about anything. But here specifically, I'll talk about the Sears collaboration, and we'll talk about how to find these stars in JWST data. So we need to identify these M, L, T, and Y types, dwarf stellar objects, or ultra-cool dwarfs, or whatever you want to call them, with photometry alone if possible, and then can we find enough of these to determine the scale height? So first things first, I've been making plots like this for a while, apparent magnitude and half-light radius, and there you get that stellar locus, that is the brown, reddish-brown points there. You can move this several orders of magnitude down with JWST. It is, to me, this plot was sort of like, oh yeah, we're in a different regime now. So you can identify stars down to 27th, 28th magnitude unambiguously, like they're point-like sources. With Hubble, for example, you're very happy when you get to 25. So there's orders of magnitude more discovery space here. So you find a whole bunch of stellar-like objects, unresolved sources, and now we're going to go see if we can identify what kinds of types they are based on broadband photometry. So there are a lot more colors in the near-infrared with JWST compared to, say, HST. And Roman as well has like this whole suite of filters that you can potentially use. So I use the Splat iSpecs or Specs Spectra catalog for this. So you essentially take all the possible types here, and you just put down the filters and see what the broad colors look like. And as you can see, there's a big absorption features here at the latest types. So these features are big enough to actually start affecting the filters, the colors. So what do local stars look like? Well, this is the sort of the color plot. So this is the color space. So this is our feature space, if you're thinking in machine learning terms. And that seems to separate out, this is JWST, because again, I've got the Sears logo in the corner there. It does seem to separate out these different types quite well. So this is starting to look good. So I've put a numerical type on there where M is 0, L is 1, and T is 2, and Y is 3, and then subtype them accordingly. And so we want a subtype. We want to be able to get closer than just M or L type, in order to get the intrinsic luminosity, so we can actually start finding the 3D structure here. So what we used to do with Hubble was basically say, oh, well, we've got this color space. Here's a block that, broad cut that's all the M dwarfs. And so as you can see, that doesn't quite translate to, it's contaminated. There's a few, the scatter, and you only get to like broad types. You can say it's an M or an L dwarf type, or is a mix of the three. So what do we do next? Well, we ask the neighbors, and so if a classification based on the nearest neighbors might be the best way to do it. Our template space is in uniformly in color space, so sometimes we have a lot of these sources, sometimes we have a few. So you just ask the nearest 3, for example, for what kind of types they are, and then you can, based on the broad colors, turn it into a specific type. So the one thing that you have to tune is actually see how many neighbors you ask in a given space. And so you can do this in not just a 2-dimensional space, but multi-dimensional space. So where is the 3 nearest sources to the one that I'm looking at? And then you just go with the majority. So it is quite important to see how many, so you have to fine tune how many neighbors you ask. So that works, this is sort of my first goes at this, and you get the predicted label at the bottom, and you get the true label at the y-axis, and so you get a diagonal when you're trying to get all the sources on the diagonal. So optimized for JWST and trying to get within about 2 types, so plus or minus 2 subtypes. You get a pretty good diagonal and not too much scatter off that diagonal. This is very encouraging, which means that I don't have to go to spectroscopy for every single source to identify it as an M2, for example. So just to visualize what that looks like, so this is the HST color plot, so 2 dimensions, that's easier to visualize. We have a particular value, you look around for the nearest neighbors, then you go to the next one and look around for the nearest neighbors, but that circle can often become smaller if it's a more denser training set. And then you go to the next one, and so that's how you can classify them. So I found a bunch of these to match late type brown dwarfs pretty well. And so there's the just like the 2 Spitzer bands. I keep still thinking of them as ARIG 1 and 2, F356 and F444. I know they're not exactly that, but you can use those 2 long wavelengths from the NIRCam to actually check up on that typing. And then, of course, JWST is a spectroscopic machine. So yes, we actually did catch one in the act. I just got this from a collaborator in Sears, and there is a very neat double absorption feature there. So yes, we can then study them in detail. So that's all that JWST can do, and then hopefully we can match the number counts to an actual scale height and typical type. What I found so far is that the M dwarfs are about 300 to 350 parsecs. It's only 1 line of sight. That's our weakness here. And the T dwarfs are 150 to 200 parsecs. So that's actually pretty neat. This aligns with what we've seen in earlier studies. So we're now going to actually put scale heights on this plot and see which one of the star formation history of the Milky Way models, that's all the lines, actually this corresponds to. Ultimately, we really want to figure out how many brown dwarfs are there anyway. And then this sort of dovetails into how many free-floating things like this are around, and that will get us the low mass end of the initial mass function. So you get the IMF, for example, for the thin disk, the IMF for the thick disk, the IMF for the stellar halo, and everything combined for the whole Milky Way. So that's sort of the ultimate goal. So Roman, can we do this trick with Roman? And so this is the LTY atmospheric models that I found, and see what kind of broad colors you get. And you can't read the axes because you don't really need to. You can say, oh, this is color, plot space again, and they seem to nicely spread out. Again, those big features do affect where they lie on a broad color space. Then, of course, I do these matrices again, and the predicted label and the true label match up okay. Notice that this is a little thicker than I'd like. So this has gone into a Roman white paper that I submitted. And so you can get to within a few subtypes. I also tried this with the actual training set, the splat data, and so that also seems to spread out nicely in broad Roman colors. And the matrix there tells me again, like, yeah, within a few types you can get onto the diagonal. And so just with the broad colors from the Roman, we can actually type MLT and Y dwarfs fairly well. So actually you can sort of set the how well you want to get to within a type, and so as you make that bin bigger and bigger and bigger, your precision, recall, and F1 go up, and so you can sort of set like, well, 80% is where I want to be, so a bin of about 0.4. So it's a little less good than JWST because just where the filters lie, it's broader filters, so we lose some of the information. But you can definitely do it. So the Roman benefits are it has excellent filters for this, for the photometric typing. We get the statistics because it's such a wide field instrument. The the benefit that I haven't talked about, but if you have recurring visits, you can actually see proper motion from galactic objects. So we could confirm that this is actually a brown dwarf from proper motion, and this is something that we couldn't do with anything before that. GRISM has the option to actually give us spectroscopic confirmation again, because we have these broad features in the atmospheres of these things. You can separately confirm the photometric typing and, for example, identify instances where this is a low mass brown dwarf. And so that would be an interesting discovery. And so we can then identify all the galactic structural components, the thin disk, the thick disk, the stellar halo, the halo streams even, and then constrain the low mass IMF for all those components separately, and then as the Milky Way as a whole. Okay, so conclusions. Step one, what did we learn from Hubble and JWST? There's a catalog for M dwarfs. There's one for T dwarfs. There's GRISM observations, and so we've been chipping away at this particular topic. We found a Sagittarius strain, for example, that shows up as a tiny overdensity in one of these fields, but you're sort of randomly sampling the Milky Way, and that does pretty well. And so you can make an MCMC model, for example, get scale heights, and you can get the total numbers. You can get a first estimate of that. And there are more HST fields to mine here, so that's a fun thing that you can definitely do. But JWST, the short color space, is already good enough to start classifying these things accurately, and then so you can actually find them further, you can type them quickly, and you can start mapping the the scale height and possibly other components with JWST deep fields for free. So this is a free science extra bonus round kind of deal. But what can you then do with Roman? JWST has an excellent filter suite to go and identify these things, but Roman suite is actually pretty good, and we're getting this again for free. I would very much like a slightly bigger training sample, especially at the later types, so more spot spectra or a bunch of more atmospheric models to expand that photometric typing. The wide area coverage means a very good handle on galactic structure. So, and we get this from all the surveys. And so the trade-off in type accuracy, but with the wider area, means that we can get a good handle on the Milky Way and what it looks like in those ultra-cool dwarf stars. So I haven't typed myself, and I'm running out of voice, but I would happily take questions at this point. Thank you.
Okay, so it looks like we have a question over here. And while the microphone gets there, are there any online?
Hi, Carrie Gilbert. Excellent talk. Thank you. Very interesting. So my question is about, you quoted, with your current training set, a delta type uncertainty of about 0.4 or so. I was wondering, in terms of time scales, what does that translate to? Is there an easy translation to as the cooling curves take this long, so a delta type uncertainty is kind of an uncertainty in age of something?
Yeah, sorry, this is all my animations have to rerun apparently. I don't quite know. I was already very thrilled that I managed to get this down to, below a broad type. Where did I put this? Essentially, we can't get it any better than 2 subtypes. Honestly, so where is it? Here. So, for example, this is with Roman. So at some point the information is not there, and so you can't get any closer than 2 subtypes. But how long that is, I don't quite know. I mean, anecdotally, I know that some of these things just basically change type as they rotate, and then the big cloud cover on the other side sort of rotates into view, and they go from L5 to L7 or something like that. So I'm not sure if there's any intrinsic scatter. I think there is, So I don't know what the actual cooling times involve. I mean, these things live a trillion years or something like that. So none of them have actually died yet. So I'd have to ask Russ what the actual time steps. I keep thinking in type steps. So type step to time step is a good question. I don't know.
Thank you.
But it was a long answer saying that I don't know.
Okay, let's go there and then there.
Hi. Also, a very good talk. So I have actually several follow-up questions on some of the methodology that you apply. So could you go back to where you apply the selections on the JWST and series view? So you quoted that you found dozens of possible brown dwarf candidates. Could there be any possibility that they can be either quasar as well?
Okay. So this is when follow-up is nice. You get a probability that this is a particular brown dwarf, right? So you saw the precision and the recall. They're all sort of. I'm happy when it sort of hits 80%, and so you never know for sure. I should probably call them candidate ultra-cool dwarfs. There's always a chance that you can have a high redshift object. In fact, this is how I got into it. I'm an extragalactic astronomer. I'm trying to get rid of these things. And so we're trying to find the right colors, color space that tells us where these things lie. And especially try to identify some that, for example, the short wavelength gives you a particular type, and the long wavelength sort of gives you a different type. That's probably indication that it is a low metallicity one. So there's all kinds of exceptions, and there could be, for example, not just quasars, but dusty, HST dark dwarf galaxies at redshift 2, for example, or we're trying to separate these things out. So I can never rule it out completely with photometry. You have to go with spectroscopy. But the idea is that in the color space that they lie, we're actually fairly confident that the majority is brown dwarfs.
Great, thank you. And just a quick numbers. So could you provide an estimation on what are the magnitudes that these brown dwarfs can be?
So I think of this particular plot, right?
But with Roman, sorry.
Yeah, with Roman. So with Roman, we go to about 25.5. It's sort of more Hubble-like, and so we can definitely find these in. I think the number densities on sky should be similar to what we've been finding with Hubble, but the typing is a little bit better. With Hubble, we've been finding. So it's about 1 M dwarf per. It's anywhere between 0 and 5 M dwarfs per WIFPIC 3 field. So it's sort of like 1 per arc minute. It's about 10 times less in the L and then 10 times less in the T dwarfs to about that magnitude. So your mileage may vary, but you'll definitely get. One of these things at least in every arc minute. So it's pretty dense. If you ask a Spitzer person about, M dwarfs and doing photometry of deep photometry of galaxies, then yeah, the M dwarfs are a problem. Does this answer your question?
Yes, that is exactly what I want.
This is very rough numbers, right? So this is what we've sort of seen in the ratio in HST pure parallels.
Okay, and we have one really quick question over here. Oh no, okay, very good.
So I don't know if you're aware, but many years ago we wrote a paper in which we used something similar with KNN to identify brown dwarfs in Spitzer and near-infrared surveys, and we spent a lot of time in the paper in optimizing the parameters for the KNN method in terms of the metrics and how to get the maximum efficiency in finding the source and rejecting what we're looking for. So if you're interested, I can send you the the
Very
reference.
much so. Yeah, that would be great. This is also for me to play with KNN. It's sort of like maximizing the information that you do have, but I hope it's clear that we get a probability for each individual object, and that you can sort of feed into a larger MCMC model of the Milky Way as a whole. So you can be not terribly confident of individual sources, but the overall model sort of takes that into account. So that's why I'm excited that our accuracy in typing is improving, so that we can actually maybe add some more components to the Milky Way structural model as you go. So it's sort of a budgeting thing. But yeah, KNN is quite powerful here. The color space is quite good at this.
Okay, so we're out of time.
Thank
Any
you.
other questions
Thank you all.
in the chat? Thank you.
Thank you all so much.
All right, and the next talk is another recording. This is Nitya Kallivayalil, and she'll be discussing near-field cosmology with Webb and Roman.
Hello, and thank you so much for inviting me to give this talk. And thank you further for allowing me to record this talk. I am actually in Australia at the moment. But I hope that, so unfortunately there won't be, I won't be able to answer questions in real time. But I really look forward to seeing you all on the Slack, and I hope we can have an active discussion on the Slack. So I'll be talking about near-field cosmology with Roman and JWST, and I'll be focusing really on lessons that we can take away from JWST and HST. So I'll be speaking about two main programs. One is the Resolved Stellar Populations Early Release Science Program. That's PI'd by Dan Weiss, with several of us as co-leads. My group in particular is working on the proper motion side of things and also the star formation histories. So there's a lot on this plot, but I just want to highlight one thing really, which is that JWST resolves individual stars at larger distances to fainter luminosities in more crowded areas and in regions of higher extinction than any other facility. So this is a Kj minus K color magnitude diagram showing a little bit about the distances to which we can reach with this facility, and which is really exciting because everything that we know about the universe is really anchored in resolved stellar populations and how well we understand them. So for example, we can do resolved star formation histories out to 5 megaparsecs. We can use horizontal branch and RLIRE stars out to 15 megaparsecs. And then we can, using intrinsically bright features like the tip of the red giant branch, which actually is more luminous in the infrared than in the optical, we can actually get TRGB distances out to 100 megaparsecs. So this is really game-changing. It allows us to put our local universe where we can get really high-resolution data into context for the first time. With JWST, we are really just doing this in a pencil beam fashion. And with Roman, obviously, we can do this with large. I'll also be talking a little bit about two HST treasury programs that are focused on all of the dwarf galaxies associated with the Milky Way and Andromeda. So this is about 400 orbits in total. Here, I'm just showing you a plot made by Eric Tollerud, focusing on the Milky Way sample, distance, luminosity, and mass on the x-axis. we actually argued to use HST sort of in survey mode for these two Treasury proposals. And I think this is a precursor of the type of work that we can do with Roman, again, with much bigger fields and getting to actually interesting statistics. So in terms of an outline for the talk, I just want to focus on a few results and some takeaways from those results. The overarching goal of my work, our work, is to probe our dark matter model on small scales. I think this is a really fruitful regime in which to understand the nature of dark matter better. And I'll talk about a project that shows a shot in the arm for our dark matter model, which is that one of the predictions of the cold dark matter model is that our universe is self-similar. In other words, satellite galaxies like the LMC and SMC should have satellites of their own, just as the Milky Way has the LMC and SMC and a bunch of things as satellite galaxies. So can we actually prove this? I'll also talk about some results from measuring star formation histories. I'll talk about the structures of these dwarf galaxies as measured from very deep Hubble data as promising probes for the nature of dark matter. I'll talk about our efforts with proper motions, and then I will talk about our efforts on the stellar evolution side as well, specifically with JWST comparisons. So first of all, satellites of satellites. So this is work that I've done in collaboration with Ekta Patel. Here's Ekta. And we were interested in a series of papers to see if when the Gaia Data Release 2 actually came out, we could identify through full 6D. So this would be an opportunity to measure full 3D velocities, so proper motions and radial velocities, which were previously known for a bunch of dwarf galaxies in the vicinity of the clouds. And their distances were known as well, so you get full 6D information, and so you have knowledge of orbits. You can measure things like binding energies and make arguments as to whether objects are bound to the LMC system or the Milky Way system. So we did this by comparison to a set of simulations. This was led by Laura Salas, and this is using Aquarius. So these are dark matter only simulations, but they have extremely high resolution. So you can get down to the sorts of masses that ultra-faint galaxies the sorts of dark matter halos in which ultra-faint dwarf galaxies reside. So in this plot, you're seeing for an LMC analog that fit the mass and the known 3D velocity and orbit of the LMC system. This is an analog from the simulation, and all these colored points show dark matter that was bound to the LMC system and is falling in with the LMC system. And we then went to Gaia and we measured proper motions, completing the full 3D velocity space for, as many ultra-faint dwarf galaxy candidates as we could in this general area, and found that a couple of them are actually coming in with the clouds. This is just showing an example of some of those systems for ultra-faint dwarf galaxies, their galactocentric velocities and distances. This is Vx, Vy, and Vz, and these gray points are ultra-faint dwarf galaxy analogs in the simulation that are coming in with the LMC and where you would expect them to fall given the LMC's orbit and velocity in this space. And then the colored points, blue and red, actually show the measured velocity and distance of these three satellite galaxies. And this is how they were identified as coming in with the LMC. And this is their past orbits over the past 4 gigayears or so. we found that approximately 7 of the ultra-faint dwarf galaxies found around the Milky Way are actually coming in with the LMC system. These show their past orbits. This legend shows the LMC in black, the SMC in gray, and it's wonderful to see, that these past orbits actually show these ultra-faint dwarf galaxies so beautifully in orbit around the LMC. So this is great. We happen to have, satellites of satellites in our vicinity. So let's see if we can push further and understand a little bit more about how galaxies really populate low-mass dark matter halos. So this is work that's been done by Elena Saki, who was a postdoc here at Space Telescope. So I'm sure many of you know her. And also Hannah Rickstein, who is a graduate student in my group at UVA, who has done all the Hubble photometry for this project. So we aim to measure star formation histories for a subset of Milky Way ultra-faint dwarf galaxies and LMC associated ultra-faint dwarf galaxies. This is just to blitz you with some beautiful color magnitude diagrams for the systems that are part of this paper. You can see that, these are some really sparse systems, and we are able to get to really individual star type of measurements for these galaxies. And then this is the result. The y-axis here is cut off a little bit, but what it is showing is the cumulative mass fraction. So this is percentage of stars added as a function of look-back time. Okay, so there's a lot going on this plot as well. So if we can just focus on this side. An interesting but sort of tantalizing at this point takeaway is that, all of these objects that we're looking at here are extremely old. 80% of their stars are in place in these galaxies, before the epoch of reionization, which is shown in each of these panels by this gray bar. But if you look at the means for these subsamples, so the ones that are coming in with the clouds as opposed to the ones that are Milky Way associated, the clouds mean is shown in gray here, okay, and the Milky Way mean is shown in black. And again, I don't want to overstate this result because it is very much, within errors, but there is tantalizing evidence that the LMC-associated dwarf galaxies are able to maintain forming stars for longer than the Milky Way system. So the LMC average, this population of dwarf galaxies is roughly 600 megayears younger than the Milky Way average. So again, LMC systems have managed to eke out star formation for longer than Milky Way systems. This is really interesting. We haven't sort of overinterpreted this particular result yet, but we are working on it. I think it jives with what you might expect, say, for a lower density in dwarfs that have been in lower density environments for longer. And I think this is a valuable way to also probe perhaps the patchiness of reionization, that there are actually the sort of importance of the local ionizing UV field. Let me move on then to dwarf galaxies as probes of dark matter. And specifically, we've been trying to ask some really simple questions on this front. Obviously, we're all after 3D and full density profiles for dwarf galaxies. And that is definitely something that I'm very excited to pursue with Roman. However, at this point, we're trying to ask simple questions, as I said, and this big question of density, whether dwarf galaxies, their densities jive with what we would expect from cold dark matter-based simulations. we've attempted to answer that here by just looking in the luminosity and half-light radius or size plane. So this is work that Hannah Rickstein, again, a graduate student at UVA, has been leading. And I just want to show one result from her work, which I think is really interesting. So again, there is a lot on this plot, but you're looking at circularized half-light radius on the x-axis and absolute magnitude in the V-band on the y-axis for a bunch of things in the Milky Way vicinity. Okay, you have globular cluster systems living up here, and dwarf galaxies living here. This gray line here demarcates our what we call ultra-faint dwarf galaxies. These are, the lowest mass galaxies that we know of in the universe, and they also have extremely high mass-to-light ratios. So these are also some of the most dark matter-dominated objects that we know of in the universe. So they fall here. And then here in this light gray, you have sort of more of a hazy border between, the globular cluster systems and these dwarf galaxy systems. We've just called them ultra-faint clusters for now. In this particular plot, we were interested to see where simulations lie. And again, Hannah has done a really careful job of doing an apples-to-apples comparison. So these are all measured in a consistent way in simulations versus in our Hubble observations. And one thing we were just interested to see is, do LMC dwarfs actually have the same sizes? And again, these are all ultra-faint systems. Do they have the same sizes as Milky Way dwarfs? They appear to. That's interesting. I don't think that we would expect them to have different sizes, but that's also what empirically the data is telling us. And another really interesting aspect of this plot that I'm struck by is all of these points without error bars are dwarf simulated in various really interesting high resolution dark matter simulations. So the legend, obviously you can look at the slide in a little bit more detail than I have time for right now. But the legend here also shows some ethos points. These are actually alternative dark matter models, specifically a bunch of self-interacting dark matter models that live up here. Also, these simulated dwarfs from the Wheeler et al. Sample using FIRE. These objects, are fluffier than objects that we've actually measured in the Milky Way vicinity thus far. Another striking aspect of this plot is here are where the classical dwarfs of the Milky Way lie. And again, there are some simulation analogs without the error bars up here as well. But this entire space is quite empty in terms of observational analogs. I don't want you to get too hung up on the number of simulated dwarfs here, because we've just put all of the simulation points on this plot. But on average, I think you're really just expecting one analog per simulation for a Milky Way type galaxy here. Nonetheless, we don't have an analog in the Milky Way system that lives here. And again, we can talk offline, perhaps on the Slack, about interesting opportunities that I see here. The only other point I want to make in this space is that, there are all these predictions, right? Is it that they are predicting something that's too fluffy, or is it that we actually just have not found them, given that they're incredibly low surface brightness objects in our current surveys? And so these are lines of constant surface brightness, 28, 29, and then this last line here is 32 mags per arc second square, sort of a Rubin and Robin type expected surface brightness that we can achieve. So I think it'll be really interesting to see if observationally we can or cannot fill out this particular space in terms of size of dwarf. Okay, moving on now to proper motions. So we've been trying to find ways to utilize cross-observatory information because you can get extremely long baselines, for example, by combining Hubble data with JWST data. And then obviously there are implications for Roman in terms of how well we can actually calibrate cross-observatory techniques to measure proper motions. And I just want to highlight a few results coming out of my group, and this is work that is being led by Jack Warfield, who is a graduate student at UVA. So typically, when we measure proper motions, you need an inertial reference frame, so something that is non-moving with respect to whatever you're trying to measure in the foreground. And background galaxies are well vetted and developed by my colleague Tony Sohn to use as inertial reference frame. What you do is, you take an image, there's a star field, there's a background galaxy, you wait some time, you take a second image, so this is a set of images separated by some epoch, and then you measure the proper motion of the target of interest as sort of the reflex motion of these background galaxies from one epoch to the other. Because background galaxies tend to be faint, and, again, I don't want to get too much into the weeds on this, but also you have to think very much about how you model them. A given galaxy will not give you, will give you a certain level of error. But what's great about galaxies as a reference frame is that you get many of them. Typically you can get something like 100 well-measured galaxies in a given ACS image. And so you get to improve on your ultimate precision for a bulk proper motion. We've been developing another approach to this in our group, which is to, instead of using background galaxies, to use foreground well-measured Gaia stars as the inertial reference frame. Of course, in this case, the Gaia stars themselves move. The background galaxies you can take as fixed. But they have known measured proper motions from Gaia, and so this is a relatively simple way to actually leverage the entire Gaia catalog for our purposes. So this is just, again, showing that in this case, the reference frame itself moves, but you can measure the proper motion by removing that well-measured known proper motion from Gaia for the foreground stars. This works really well for Milky Way classical dwarfs. This is showing a result for the sculptor dwarf spheroidal. This is proper motion in the right ascension direction. This is proper motion in the declination direction. And these are our results here compared to some other very well vetted results from the literature. Again, using our result is using Gaia foreground stars as the inertial reference frame, but measured within two Hubble images that were separated by a given baseline. So you can see that there are in terms of classical dwarfs like Sculptor and Milky Way type exposure times, you get a bunch of Gaia stars that you can average over, and this works really well. This is our attempt to do this now for one of the targets of our result stellar populations program on JWST Draco 2. Okay, so this is an HST to JWST measurement of Draco 2's proper motion. Draco 2 is at roughly 20 kiloparsecs, and it also, this is about a 6-year baseline between the HST and the JWST observation. So what's striking here is that this is our result. Okay, so this is the earlier result. This is from Pace et al. Using a combination of Gaia and their own methods to actually add additional members from other surveys. using a very sophisticated technique. And then this is our cross-observatory result for the moment, which has larger errors, though, it is consistent with this measurement within the errors because of the fact that most of the Gaia stars in our JWST images are saturated. So these are really the only stars that remain for use that are not saturated. So, and this is a sort of larger issue. This is a really easy, relatively cheap technique to use to measure proper motions for any given field with 2 epochs of space-based imaging. But we have to think about not saturating the reference frame. So we have to think about strategies to do that. And this will be relevant for Roman as well. This is now, because we were not finding that many Gaia stars, we attempted to actually add galaxies as well to see if we could improve on our precision. So what's great about the JWST filters is that a combination of short and long filters actually very efficaciously separates stellar sources here from more extended sources, so galaxies in this cloud and stars in this cloud. So if we use the color information to choose likely background galaxies, but then we're still using a PSF at the moment to fit the center of these background galaxies. And if you just do an average, you get to add a lot of galaxies, which does, improve the precision. But there's still, I think, a lot of work to be done in calibrating the use of these galaxies in order to do this well. We have to think about how we fit their centers, and we have to think about ways to mitigate the fact that these sources are actually just intrinsic. They look different from optical to infrared filters. And so when combining an optical and an infrared image with galaxies to make a proper motion measurement, we have to actually take that into account, that your inertial reference frame looks different. There are different stellar populations that are being, highlighted in each of those filter sets. So in this, as part of that, we're developing a Bayesian approach to this, where perhaps you can let the stars, the Gaia stars, sort of, as a input in the fit, and also allow terms that could hone in on this difference in morphology when we're fitting galaxies. But this is work in preparation. And I just wanted to point out those two things. One is we have to think about the profiles of the reference frame that we use for proper motion work. And we have to come up with ways in which we will not saturate Gaia foreground stars that could really help us in doing this with Roman. Okay, and then finally, I think I am out of time. So let me, I have 4 minutes left. So sorry if you will bear with me going a little bit fast. I just wanted to come back to our JWST work, and this is highlighting some work done by Dan Weiss, Christine McQuinn, and Chris Garling, who is the UVA Near-Field Cosmology Fellow who's working in our group. So first of all, I wanted to just quickly point out a few things from some of our early release science work. This is on globular cluster, the globular cluster M92, which is at a distance of about 10 kiloparsecs. And here you're looking at JWST CMDs. And I just want to point out here that this double main sequence is actually module A and B 0-point offset. Understanding chip calibrations is actually essential to this work. Here is the hydrogen burning limit. Using something like Roman, you can really reveal the full spatial extent of globular clusters. And you can go down to the hydrogen burning limit and explore things like tidal features, gradients in binary stars, and multiple populations. And then this is now WLM. This is another focus of our ERS work. This is showing some really exciting work on star formation histories led by Christie's group and then also by Chris Garling at UVA. This is WLM, and this is actually the JWST field. Okay, so up here you can see the half-life radius of WLM and where we currently have coverage from HST and JWST overlap. So the first point to make is that Roman can provide, deep CMDs for entire nearby galaxies, and things like population gradients, for example, within and without this half-life radius here would be key for testing feedback in galaxy simulations and understanding the coupling between baryons and dark matter. But the great news about this work is that this is showing you a star formation history for this field of overlap between ACS and NIRCam. And the takeaway is that this agreement is great using, ACS with really well-vetted techniques, and NIRCam, which now, we need to prove sort of the validity of stellar evolution models in the infrared, but that all seems to be working really well. There's very good agreement between star formation histories recovered from the ACS field with the NIRCam field. And this is showing some of Chris's work, showing the JWST, NIRCam, WLM data, his star formation history model, and then a data minus model in this final third here. And again, this module for star formation histories that he's been working on should be available and ready to use by the public in the not too distant future. But I will just end my talk here very quickly with these takeaways. The universe is in fact self-similar. We have found dwarf galaxies of dwarf galaxies. Ultra-faint dwarf galaxies, I think, are a promising frontier in testing feedback models, and that luminosity size plane is a good space to understand whether, we are producing realistic dwarf galaxies, and this will really be enabled in a huge way with Roman. Proper motions, utilization of short exposure observations will play a key role in expanding the number of available Gaia stars. Again, a really, I think, powerful tool that we need to make sure we work with Roman, because, this is a way to measure proper motions in every field. Population gradients, again, coupling between dark matter and baryons will be done writ large with Roman, and we've proved that stellar evolution libraries are their sensitivity and accuracy are working well in the near IR filters in relation to the optical filters. I'll stop there. Thank you so much for your attention, and I look forward to hearing from you on the Slack. Enjoy the conference.
Okay, so that concludes session 3, surveys within the Milky Way and nearby galaxies. Let's give a quick thanks to all the speakers. And now we will begin session 4A. Okay, so let's welcome Cosmin and discussion on using Roman to find dark star candidates.
Right. So first, I'd like to start by thanking the organizers for giving me this opportunity to tell you about the subject that has been fascinating me for a while, and I hope by the end of this 15 minutes I have, you would be at least intrigued, right? Now, the title of the talk, I'm not going to read it. You might see here the void in which the Roman is piercing or peering. The void means the many mysteries that I hope this telescope is going to help us elucidate. Many of them. some of which potentially dark matter, or even what I call dark stars. But let me use this slide to clarify what dark stars are not. Okay? First of all, they are not dark. They could shine as bright as a galaxy, so definitely they are not dark. Second of all, they're not made of dark matter. It's about, yes, Michael? I think it is, but if you can't hear me, I don't know if it's loud. See? Well, I'm not going to repeat what I just said. Hopefully, in the back, did you all hear me okay so far? All right, good. So they're not made of dark matter. Dark matter may be part of them, about 1% or less, right? So they're not dark, and they're not made of dark matter. Now, maybe I can turn this on or not. I'll proceed like so. A lot of beeps, so I need some help. Yep. All right, there we go. There's something else they're not. They're not a spoof movie to the 2001 Odyssey, a movie that I think all of us should watch some point. But let me proceed to the actual science I want to discuss with you today. All right? Now, to motivate, and to go back to the title of this conference, which has in it inspired by web emerging results, I'd like to ask the following question. Did the web already see those objects? And hopefully by the end of this talk, I would have convinced you that potentially, yes, the web might have seen dark stars, right? I need to present a little bit the idea of this dark stars. I already mentioned the word 20 times already, but let me tell you what they are. They're a hypothetical as of yet object that those guys could form whenever the first stars form in the conditions of, high redshift versus 20 or so, where the first stars are believed to form. In the simulation here on the left, you have molecular clouds collapsing. This is a standard picture taken from Roman 2009. A competition between gravity and heating. Eventually, you emerge with an object in hydrostatic equilibrium, the protostar, so on and so forth. Now, in the standard picture, dark matter annihilations is not included, and you end up with an object that will eventually shine because of nuclear fusion, right? The question that was posed by Fries, Gondolo, and Spolier in 2007 was, well, could this standard picture be modified if we now include effect of dark matter heating throughout this collapse of a molecular cloud picture? And the answer they found is, yes, indeed, this picture could be modified. Well, I need to learn left versus right, first of all. And they found the three conditions upon which you no longer can, the collapse of this molecular cloud is stopped many orders of magnitudes in density before any sort of nuclear reactions can take place, right? The three are, you have to have sufficiently high dark matter densities, which in the early universe, those microhalos do have high dark matter densities. Second of all, you have to have poor cooling, but remember, those are pristine BBN gas clouds, zero metals, so really the cooling is the worst you could ever have. And third of all, this is the particle physicist kind of insertion in here that dark matter annihilations products have to be trapped inside. We really found that typically within WIMP models, they're really well efficiently trapped, right? So now those objects could actually form in the early universe as evidenced by this paper in 2007 I mentioned. Now let's build them up in mass a little bit, if you will, to the supermassive dark stars, which are the main topic of my talk today. This is an HR diagram, no need to explain it, but suffice to say I have three different masses for the WIMP, 10 GeV, 100 GeV, 1 TeV. All those annihilate with the same thermogenic annihilation sigma V. You all know the standard WIMP annihilation cross-section, right? Some takeaways, the lighter WIMPs, which are in dark here, are more efficient in heating up this object, which is natural. And takeaway, they really can build up in mass as massive 10 to the 5th or more solar masses. In other words, they could potentially accrete most of the baryons surrounding them. The main reason for that, if you look at this axis on temperatures, they're cooler than roughly 10 to the 5th, or actually much cooler than 10 to the 5th. So accretion is not shut off, right? They don't emit enough
ionization radiation to shut off accretion. That's one mechanism to build a mass. We call it extended AC. And how to motivate that? Typically, dark matter halos are triaxial, meaning they would include a lot of orbits that pass arbitrarily close to the center. Now, another way to build a mass is, let's say you are living in a halo that's not triaxial, and initially you have a reservoir of dark matter that's exhausted. Then you follow this phase of a Kelvin-Helmholtz collapse. This object is contracting, could potentially even lead to a main phase. But if the dark matter ambient density is high enough, you're going to end up with a efficient capture of dark matter inside this object, which would again lead to a dark star phase, now powered by captured dark matter. So we have two distinct scenarios upon which we can build a supermassive star, 10 to the 5th or more solar masses. But look at here, they can be as bright as 10 to the 9 or more solar luminosity. That is a single star that's as bright as a galaxy. You know that? And we can see them, actually. So, why do we care about this object? Not because we can build them, but they could actually solve long-standing puzzles in cosmology, such as this mystery, you know, where do those supermassive black holes that power the many, many distant quasars at high redshift come from? And, you know, people have to invent non-standard theories to explain those guys. They could either say, well, we accept supermassive accretion, which is fine. They could invent mechanisms to do that. Or they could say, well, we need a supermassive seed, because pop-free stars as seeds are not massive enough to generate those objects, right? So that's a thorny issue, but if dark stars are a thing, then they could collapse absolutely to black holes, right? And they would provide those seeds for those objects. Moreover, the Webb started to thicken this plot of what's happening in the early universe. To the point of, I mean, here I have the 6 Lambda galaxies that were quote-unquote breaking the Lambda CDM. Not really, but still, that's what the popular press was claiming. Okay, the galaxies that broke Lambda CDM. But anyhow, those are representative of a problem that Webb data is giving us, or making us face. There's too many, too massive, too early galaxies, or quote-unquote galaxy candidates that are observed, right? And that is a puzzle. That's really a puzzle. And namely, if you assume that those are indeed galaxies, that means their stars inside of them have to have converted, the gas has to have converted to stars about 100% efficiency, which doesn't really happen in models unless you think about a dark star. Those guys really can accrete the baryon surrounding them because they're cool very efficiently. Moreover, very quickly about, I'm not going to go through the paper, but it's a paper written by Kamiankowski and collaborator that basically shows that if we're to say, okay, the puzzle presented by the Webb data in terms of early to massive objects, we try to fix it with extra outside of Lambda CDM cosmology. Can we do that or not? The answer is yes, you can, but then you would be in contact in tension with the Hubble data, right? So Lambda CDM outside of Lambda CDM is not how you solve this tension. Now, quickly, do we observe or not dark stars? The main takeaway I want you to have from this talk is that we have candidates right now, 3 such candidates. We uncovered them in a collaborative work with Gillian Pauling and Katie Fries. And basically, let me skip this slide. This is details you can ask me at the end. Here, you all have probably seen this, is the JADES exposure, right? And the 4 JADES objects identified back in early 23, right, by the JADES collaboration. One of those is the most distant, quote-unquote, galaxy ever confirmed spectroscopically. So we have spectra, and this galaxy is redshift of 13. But now we can feed it. So we've done the same analysis to feed this with the dark star spectrum. And yes, indeed, it feels really nicely. The JZ is 13, so does JZ 12, so does JZ 11. And we really didn't try that hard. In other words, our mass grid was rough. It was really coarse mass grid. And basically, we found that generically, we can feed those photometric data from the web with dark stars, right? That's the main takeaway. Dark stars, supermassive dark stars are generically very good fits for the web data, okay? Now, there's more things to do. It's spectroscopy, because you see this thing here. It's a helium 1640 absorption line, which is not present in early galaxies. So with high enough spectroscopy, we could potentially have a smoking pan signature of those substances, all right? And I'll just leave because I think, am I out of time already? Probably yes. And I don't want to eat into the nice conversation we're going to have later. I'll just leave with this slide here. And I think the main takeaway is like right now, having a Lyman gray, in view of what I told you, should no longer be viewed as sufficient as claiming this is a galaxy. Because I can probably fit up with supermassive dark star generic, you know? So the main takeaway, we need really high quality spectra to be able to tell them apart. And with the web, we can get spectra. What could Roman do with a wide field of view? It would give us a lot of candidates, and we could interplay that into spectroscopy with other instruments such as the web, right? So now we really need high quality spectra. I'm going to stop right here to give a chance for comments, questions, and then obviously to move on to greener pastures for the discussion.
All right, right there, third row.
Great talk. So from the SEER survey, we've been finding candidates that are point sources. Some of them have redshifts that are high, but not as high as 13.
Right.
But they have red and blue SEDs. They're red, red end and blue there. Is there any way to get that kind of SED?
We were trying to think of that question is really bugging us for a while now. How do you get the reddening? How do we say, okay, dust, but where's dust from? Or maybe could be one of those dark stars dominates the SED in terms of it already converted to a black hole, and then you have some stellar. But this is just speculations right now. I'm just speculating. I didn't do the science yet, but this is a great question. Thank you for asking it. Yes, we need to address it properly to figure out how can we get the reddening. Yes.
Okay, we have one more, as long as it's short.
Well, I hope so. I just wonder if there are any other, what is the signature of dark matter annihilation? What, it gives off energy, obviously. Is this mostly very high energy?
Right.
Because, dark matter still exists today. We should, in theory, see some evidence of this if it really is happening.
I see. Another excellent question. So there's some signatures of, people claim that at the center of the galaxy, there's some excess there, right? Which they actually fit it with the coastal wind. So one thing we could do, we've never done it, but I think we should do it as the people that work on dark stars. Let's try to take those parameters that feed the excess galaxy and port them to a dark star and see then what can we do with the distant stars, But that's a good question. Thank you. And I don't know if my answer was short enough, but I will just stop there. We can talk more later. Yeah.
Perfect.
All right. Thank you.
All right. Perfect. That is the end of this talk, and we will begin some discussion now. So thanks for all the speakers this morning. You all did fantastic. Loved all of them. You deserve a huge round of applause.
Thank you. So the discussions will actually happen in the cafeteria if you want them to in person. So we have 6 topics, actually 7 with your own adventure. The topics are on Slack, but I will quickly read them just to make sure you can go pick. And this is how those are taped on the cafe. So topic 1, Roman's core community surveys are going to be defined by a community process. How do we as a community want to be able to engage with this process, and what do we want to see come out of this process? So that's question number 1. Question number 2, what are your plans for dealing with the torrent of data? Question number 3, Roman data will be accessible to everyone with no proprietary period. How then will we approach crafting general astrophysics surveys that enhance the overall legacy value of the Roman data rather than addressing focused scientific inquiries? What are the most exciting prospects for Roman for exoplanets? 4. For the Milky Way and nearby galaxies, 5. Galaxy evolution, 6. And choose your own adventure, 7. So go out and mingle and pick a topic. The discussion session will happen again on Friday. Please select someone to synthesize your thoughts, as that will be presented at the summary session on Friday. So if possible, pick someone who will be here Friday. That's all. Please go on and chat.